So data management is basically made up of a two-part process. We have our organization side, which is all the sorting and organization of data. If you're Google, that's also consists of things like caching certain things like sites and whatnot. But then the second side of data management is searching for what you actually need. And one actually requires the other to exist for the most part if you want to do it effectively. So we've covered a ton of different sorting algorithms in this course, and we've seen even more than what we've actually went in detail on. And of course, we saw that some suit different situations better than others. Now we're going to move on to searching. And the thing is, with searching data, we really only have two ways to search basic forms of data. Now that being said, of course, there are tons of other search algorithms and search methods out there. For example, Google doesn't use what we're about to cover to search the internet for what you want. It's just not even remotely fast enough to search billions or even trillions of websites for something in the speed that you need it. Now, when you type something into Google, you'll get 1 million results in a fraction of a second, and they're actually displayed on the screen for you. What we're doing doesn't really work like that because they're using completely different strategies. And if you want to read into that, you can Google how to Google. You can Google how Google works very easily. But their method has actually changed over the years, far different than what they used to do way back in the late 90s, early 2000s when they first started operating. So do some digging and more look on how it evolved over time, because that's really what matters. And you can see all the different implementations and all the different refinements that they did. Now we're covering basic data searching today. And there are two main algorithms when it comes to this. The first algorithm is something called a linear search. So a linear search, that's what we're going to cover first. And the next one we're going to do after that is something called a binary search. Now, we've already heard the term binary a few times in this course. More notably, most recently, I should say, is when we discussed binary trees, also known as binary search trees. Now, they're not quite the same thing, but a binary search tree is basically a tree that makes sure that its structure is optimized for a binary search, which is what we are going to be covering next. So let's start off with the linear search algorithm. Now, a linear search algorithm is something you've already been working with this entire time. You just haven't had a name to apply to it up to this point. You have an array and you need to find a piece of information in that array. How do you do it? You write a for loop and you go through every element one at a time until you find what you're looking for. That's a linear search. Why is it called a linear search? It's called a linear search because when we break down the time complexity, it's a linear algorithm, which means it's big O of n time. Why is it big O of n time? Well, because potentially speaking, in the worst case scenario, the data you're looking for doesn't even exist in the collection. So let's say we're looking for 47. If we're looking for the number 47, the algorithm says start at index 0. Does the value at index 0 match my 47? No, it does not. So move on to the next one. And then it's going to continue this process, looking at every single algorithm and failing and failing and failing. It gets through all of them, all n elements. So that means it looked through every single element possible, which means linear time. This obviously is not ideal situation, but it does actually function the way we need to. It's going to find the data you want if it does exist. It's just not going to be super quick. Now, that being said, if you're working with a very small data set, it's perfectly reasonable. If you're only working with 10 elements or whatnot, there's no reason not to write a quick for loop because it's short, very little effort, and at 10 elements, you're never, ever going to notice any form of change in terms of efficiency, unless of course you're repeating that action over and over and over and over and over again, and then of course you want to optimize it. So again, the algorithm is very simple. Look at the first index. Does the value there match the value you're looking for? If not, move on to the next one. And repeatedly go through this process, iteratively using a simple for loop. Usually it's something like for int I is equal to 0 such that I is less than your array dot length. So you get to each one, I++, and you're just comparing it the whole way. Linear search. Now, there is actually benefits to linear searches that don't exist with other types of searches. The number one benefit is you don't have to sort, because it has to look through every single element anyway. So there's no real need to sort the data. It could be just as easily in the first element as it could be in the last element. It doesn't make a difference. So it's still got to go through the whole process. So sorting is not necessary. That's great, if that's really what matters to you. Now, in terms of time complexity, I mentioned that it is big O of n time. What about space? Well, space-wise, it only requires, well, nothing. Absolutely nothing. You're just comparing data the whole way. You don't need to store a single value unless, of course, you count your counter variable in your for loop, in which case that is still constant because it's one counter variable regardless of the size of n. In which case our memory, our space, would require big O of constant space. Great. And whereas our time complexity is big O of n. What does that mean, big O of n? That means if n were 1,000,000 elements, that means that it would take 1,000,000 operations to find our data in the worst case scenario. Now, the worst case scenario is actually two worst case scenarios. If the value is either not there or if the value is in the very last element. In either case, it has to look at all n elements to actually find the data. So we're looking at big O of n time. Now, 1,000,000 operations to find a piece of data is unacceptable when you're dealing with large amounts of data. You need to find another way. So in order to accommodate this, people have discovered a different way, a way that you have been using your whole life in various situations, and you probably don't even realize it. So let's take a look at what I mean by that. So first of all, let me paste in this here and just kind of move this around a little bit. So here I have the exact same data that we had a second ago, and I'm going to work in blue pen so we can separate everything here. So this is going to be our linear search. Okay, let me just increase the size of my pen size here so we can see it a little bit clearer. So our binary search, sorry. So what does this actually mean? Well, imagine for a second that you wanted to go to, let's say you're going to Best Buy and you want to go buy a new movie, a new Blu-ray or whatever, and you're looking for your favorite movie. Maybe it's your favorite Christmas movie or whatever the season is. Maybe it's the end of the school year and you're looking for your favorite summertime teen flick or whatever. You know the movie you want. You get in there and you notice that they're all organized by alphabetical order. What do? Well, you don't start at A and work your way over. That would take you forever. That's a linear search. What you would do is you would look at the letter that you're looking for. So let's say the movie you're looking for starts with an M. Well, that's roughly in the middle of the alphabet, so you would go find the middle of the movies. Roughly, you would even eyeball it. You're like, oh, this is about the middle, and you would check, and you say, nope, this isn't far enough. This is only, for example, the G's. So I got to move farther over. So you would move farther over, and you would look at the next, and you would try and find it more accurately that way. If this were the 80s and you needed to find a phone number in a phone book, maybe even the 90s, I guess, you don't start at the middle of the phone book. You start about halfway, and then you check to see whether you've gone far enough. If not, you go to the left half. If not, or if so, if your name you're looking for is bigger, then you go to the right half. It's all about organizing and finding where you should be based on your starting point. If you start at the beginning, you're going to have to scan. The better way to do this is to find that midpoint and then compare what you're looking for with that value. So why do we use binary search? We use it because it's intuitive. It's something that we just naturally do. We know we got to go a certain distance through the data, so we start going through that distance. The second reason we use it is fast. Not a little bit, extremely fast. Ridiculously fast, as you're going to see soon. So the one caveat is that your binary search will only work on sorted information. Now, the cool thing though is what I'm looking at here is a sorted array. This could work just as well on a binary search tree. So for example, if I had a binary search tree that represented the same data, so let's say 45 was in the middle, and then on the left we had 31. Actually, no, let's do 24 here. 24 right there, and then we got 31 right here, and then we got 17 right here, and then on the right hand side, Maybe you have, let's see, 52. Yeah, let's go with 52 right here. Oops. 52. And then to the left of that is going to be 50. To the right of that is going to be, I don't know, let's go with 96. And then to the left of that is 63. Not a perfectly balanced tree, but close enough. Now let's look at the steps. How do we actually do this? If you were looking at this binary search tree and you wanted to find, let's say we want to find 50. How would we do that in this binary search tree? Well, we know the rules for binary search trees. The binary tree says if the number we want is bigger, we go to the right. If the number we want is smaller, we go to the left. Well, we got to check the number we're on first, though. So is 50 equal to 45? No, it's too big. So we move to the right-hand side, and now we compare it against the next one. Is 50 equal to 52? No, it's too small, so we move to the left one. Oh, is 50 equal to 50? Yes, it is. So it took us 3 checks. Now think about, let's back that train up a little bit and think about what actually happened here. If we think of this logically, we said, is 50 equal to 45? No, it's not. We got to go to the right. But what happened to all the stuff on the left? We literally just cut it off and said, we don't need you anymore. We only care about the stuff to the right. Now, if we're looking at our array, what does that actually mean? It means we're going to basically ignore half the array every single step of this process. Okay, so let's look at the actual algorithm to solve this problem then. What does this actually entail? So here's the steps. I'm going to draw a line over here and we'll write the steps in red. Step number 1. Find the midpoint. Now, what does that mean? So here's what you need. First of all, it requires that we are given 4 things really. We're given 4 things. We're given the array to search on. Makes sense. And we're given a left and a right index. A left and a right index. So these are the 2 index values that we're going to search between. So in this case, it'd be 0 and 7. And we're also given, of course, the value that we're searching for. Let me just write that down below a little bit. We're also given the value that we're actually searching for. So using this information here, now let's look at that and bring it over here to the side of our algorithm. So the first thing we want to do is we want to find that midpoint. What does that actually mean? Well, that means your left plus your right divided by 2. So in our example over here, on the very first step, step number 1, we got to find that midpoint. So what is that midpoint? Midpoint is going to be equal to our left, which is 0, plus our right, which is 7, divided by 2. Now there's no decimals allowed, so we know it's 3.5, but we're working with integers, so the 0.5 gets truncated, so that equals 3. So index 3 is our midpoint, not the valued index 3. Index 3 is itself our midpoint. Okay, so that's step 1. Step 1 is find the midpoint. Okay, now inside, really there's only one step, but that's okay, we're going to break this down. Inside of this, we are going to compare the value at the midpoint against the value we're searching for. So we're saying, is our value greater than, is our value greater than the value at the midpoint? So our, let's say, array at the midpoint. I'm just going to write mid to shorten it up a little bit, otherwise we'll be here all day. So is our value greater than the array at the midpoint? If it is, that means our number is bigger and we got to look at the right-hand side. So what do we need to do in this case? Well, we need to recurse. This is a recursive algorithm. So we're going to recursively search with a new left point. With a new left. What is the new left? Well, we know that our number is too big here. So in this case, what is left going to change to? Does right need to change? So now our left is going to get recalculated at mid plus 1. In this case, it's going to be 3 plus 1, which equals 4. The right does not change because it's on the right-hand side. It's okay. We don't have to do anything. So now when we recursively call, left doesn't have the value 0 anymore. Left now has the value 4. So that's important to remember here. So over back in our rules again, the rule says if the value is greater than the array at the midpoint, then we need to recursively search with a new left of mid. You know what? Let's write that in green like we did before, of mid plus 1. Okay, but what if the value is less than? So if the value is less than the array at midpoint, then we need to do the opposite. We need to recurse again, so recursively search. With a new right, because this time we have to go to the left-hand side of the midpoint. So what is the right going to be? Well, it's everything up to but not including the midpoint, so the right is just simply mid minus 1. But we missed the most important step. What if the value is equal to the array at midpoint? Well, this is the most important thing. What do? Well, we're done. We're absolutely done. So in this case, we return the midpoint. Not the value at the midpoint, the midpoint index. So midpoint index. So these search algorithms, they don't return the actual values. They return the index of the values found at. Now this is great, but what if it never finds it? What if it gets through the entire thing? Well, that brings up the final process. So the process continues. The process continues until when? Well, until the value is found. But what if the value is not found? That brings up the or. Or, the size of the range being recursively searched for is 0. Or the search size is less than or equal to 0. Really, that means your right index is less than or equal to your left index. That's what it really boils down to, right? So we can write this down as saying right is less than or equal to left, because that means you're searching through data that doesn't really exist. So we have our algorithm on the left here. Let's follow that algorithm and solve the problem on the right. So what we did here is we said we found the midpoint, which was 0 plus 7 divided by 2, which gave us 3. And that gives us index 3. And then the first step we have to do is, let me just erase this part right here, because that's getting ahead of the curve here. The first thing we have to do is we should check to see whether our value is equal to the value of the midpoint. Now we're trying to find 50. Is 50 equal to 45? No. So it fails that. So it says we need to calculate a new left. So the new left is going to be equal to mid plus 1. I know I just erased this, but that's okay. Which is going to give us 4. So now this is our left index, and our right index is still at 7. So it goes in and it recursively searches now on this section. Okay, so now we're sitting here and we're at 50, 52, 63, and 96. And that's index 4, 5, 6, and 7. So we come through again, and step number 1, we got to find the midpoint. So the midpoint is our left, which is 4, plus our right, which is 7, divided by 2, which is, that should be divided by 2, not 12, divided by 2. That's looking very awkward, so I'm going to erase that and fix that up a little bit. We'll just write it like this, divided by 2. And what's that equal? Well, 4 plus 7 is 11, divided by 2 is 5.5, so that gives us 5. So that means our new midpoint index is index 5. And our next step is, does the value at index 5, which is 52, equal the value we're looking for? No, it doesn't. So we still haven't found the number. Is our number less than? Yes, it is. So we got to calculate a new right index this time. Okay, so we got to calculate a new right index. So our right index is, our right index, oops, let me erase a little bit. Our right index, where's my, red pen. Our right index is going to be equal to mid minus 1, which is going to be equal to 4. Okay, so now that means that we're looking at a piece of data that is, the next step is going to be just passing down index 4. So our size is a whopping value of 1. Sorry, this should not be less than or equal to. This should just be strictly less than down here. I made a mistake. Let's just fix that. Right would have to be less than, because if right was equal to left, that means that we have a value, we have a size of 1, which is a perfectly reasonable size. So we got to start over again, and we say, okay, got to calculate our midpoint. Yes, it still goes through this, even though there's technically only a size of 1, right? Of course, there's shortcuts that you could make. 4 plus 4 divided by 2 is, of course, going to give us 4. Great. And it looks at it and says, well, is the midpoint value equal to the value searched for? Yes, it is. So midpoint value, so let's write this out. So value, that's not working out. I'm going to clear this up a little bit. So value is equal to our array at mid. This is completely correct. So what do we return? We return mid. We are done. So it found it again in 3 steps, the same way. If we look at this, it took 3 steps, the same way that the binary search did. The binary search failed on the 45, went down to the 52, failed on the 52, went down to the 50, and found it. And that's because it's the same algorithm. It's just done on an array versus a binary tree. It's the exact same structure. You're cutting off half the tree every step. Here we're cutting off half the array every step. Both are completely equal in time complexity. Space complexity is a little bit different depending on how you do things. But let's measure our complexity now of this whole thing. In terms of space complexity, what are we looking at? If we're looking at our binary array, our binary search algorithm using the array, well, there's 2 schools of thought here. School number 1 is that you pass in a brand new array every iterative step. So you're passing in a brand new array that's half the size of the array. Now, in the worst case scenario, the data doesn't exist, which means eventually you're actually creating twice the amount of data. So your space efficiency, let's, what color am I going to use here? We'll just use black. So in terms of space, in terms of memory, if you are passing the array, you're looking at big O of n memory. You're doubling your memory. That's not necessarily a great thing, but it depends on your implementation. However, if you're doing it this way that we specified here, where you have the array and you pass in 1 left, 1 right, and the value, well, those don't depend on the size of the array. So what we're looking at here is big O of 1 if you're just passing in indexes. Okay. But what about space? What about, or sorry, not what about space, what about time? How does time change? Well, let me create a little bit of space here and we can discuss this. So space here works exactly the same way as it did with the merge sort. What are we doing every step? Well, we're dividing the array in half every single step. So, because what are we trying to do? Well, we find the midpoint, and then we're saying, okay, well, we got the midpoint. Which side do we need to check, the left or the right? So we're always taking away half of the element. Well, that's a divide and conquer strategy. And we went through this and we said, well, that's an inverse exponential relationship. Now, if you remember from our merge sort, lesson, what that basically broke down to is we ended up with an algorithm that was this complexity. It came down to n is equal to 2 to the y, where n is our number of elements, and y was the number of divisions. the number of divisions by 2. Number of divisions by 2. And the by 2. And the 2, of course, comes, that's where the 2 to the y comes from. Right? So, for example, if we were dividing by a different number than 2, say by 4, then that would be n is equal to 4 to the y. But that's not what we're doing. Right now, we're just dividing it by 2 every single step. All right. So from there, we rewrote that algorithm to y is equal to log base 2 to the n. Now, base 2 is a unique situation. Normally, logarithms are base 10. So the math can get a little bit more complicated, but it's still the same idea. So what this boils down to, ladies and gentlemen, is that our entire search is this relationship. Our entire search is a big O of log base 2 to the n algorithm. Usually we just write that as big O of log n. That is so ridiculously incredible, you wouldn't even believe it. So let's do the math on this. What does that actually mean? So if n is equal to 1,000,000, just like we did with the linear search, and when we did this with the linear search, we found that it still took 1,000,000 operations. If n is equal to 1,000,000, how do we do this math? Well, we need to calculate log. So basically we're saying, what is log base 2 of 1,000,000? Well, your calculator typically won't do that. So what you need to do is you need to do change a base method, which turns into this. Log base 2 of 1,000,000 is going to be equal to log base 10 of 1,000,000 divided by log base 10 of 2. And when you do that math, this comes out to, wait for it, 19.9. Let that sink in for a second. 1,000,000 elements requires about 20 operations. We just finished testing 1,000,000 operations to do it with the linear search. This is why algorithms like this and the data organization is so important and so powerful, because we can find that data in a very, very quick process. And that, ladies and gentlemen, is a binary search. Hopefully you grasp the true power of this type of thing and will be able to apply it going forward. Good luck. Take care.